If I click on economics, I can, as I said, for my project, I can change the economics parameters as well, like nominal discount rate, if there is any for any country, or the expected inflation rate. For example, it is various for different countries, and then you, depending on the location site, you can also change these. Project lifetime you can change, and if you have some fixed capital cost or fixed operation and maintenance, and even if you want to change the currency of the costs, for example, I'm going to change it now to euros. Let me see, yeah, like that. And then if I go to the next tab, constraints, you can see that if you have any annual capacity shortage constraints, you can also add it here. If you want to have a fixed dedication of renewable energy into your system, you can also add it here in this minimum renewable fraction. You can say that, okay, 10% or 50%. It means that I am obliged to produce my energy, about 50% of my energy I am obliged to have it through renewable sources. So you can also choose this. And yeah, the other ones are not so important for now. Let's go to emissions. For example, if you have a generator here, a diesel generator here in this system that we so far implemented, and if we produce or if we emit carbon dioxide or carbon monoxide or other harmful gases or other emissions, if we have something in our system, and then if we are obliged to pay penalties for them, in per ton of this emission, so we can also add the cost for this penalty. For example, if I produce 2 tons of carbon dioxide, for example, in this system, just consider it as an example. It's not that correct, but I need to pay for each ton of it, for example, I don't know, 1,000 euros. Okay, so you can also add these numbers here as well. So this was the introduction of the software so far, and as I said, of course you can play with all the areas in this software and then find more about that, and then maybe you can find other interesting stuff as well. So next part, I'm going to solve the tutorial number 6, which is already solved in your tutorial sessions with Professor Krauter, and I'm going to implement and simulate the exact example in HOMER Pro, and then see about the results, and then just compare them with what you have achieved already. I'm going to pause the video right now, and then I will bring the tutorial question one more time in front, and then I will start implementing that. Okay, so I have found the tutorial, exercise 8. Sorry, I guess I told you exercise number 6, but okay, there was exercise number 6, but now it's with HOMER, so it has a new number, which you can find this exercise, and then I'm trying to simulate this exercise into HOMER. So the question says, an off-grid household in Rio de Janeiro with daily irradiance at worst months of the year, 4 kilowatt hours per square meter per day, has the following electrical energy needs: 1 ventilator of 60 watt operating from 9:30 a.m. until 11 p.m., 5 lights of 60 watt each operating from 7 p.m. until 11 p.m., 1 notebook computer of 30 watt operating from 6 p.m. until 9 p.m., 1 TV set of 100 watt operating from 8 p.m. until 10:30 p.m. Calculate the load respectively daily consumption to be supplied after energy saving measures. In the next part, the lamps will be replaced by LED lights. And then calculate the battery size with a 24 volt system, battery cycle efficiency of 80%, efficiency of charge controller equal to 95%, and inverter efficiency of 90%. And then calculate the panel size with PV conversion efficiency inclusive PR, performance ratio losses, is about around 10%. And we need to calculate the costs afterward, which in case PV panels cost €1 per watt peak for lifetime of 25 years, battery for €300 per kilowatt hours for lifetime of 4 years, and mounting and support structures of 50 cents per watt peak. And then the second part says that 5 lights of 60 watt each operating from 7 p.m. until 11 p.m. 5 LED lights of 8 watt each have the same luminance. So we want to see how much is the difference in energy that we need to provide first for conventional lamps and for in case of LED lamps. So now I'm going to start the simulation in HOMER. Okay, so this is completely a new project in HOMER. First of all, I need to enter the input data that I have from this exercise and then run the program to see what happens with the results. Okay, so an off-grid household. First of all, an off-grid. It means that it is not connected to a grid. So that means we don't have any grid connected. This component we don't need to add it. And in Rio de Janeiro. So first of all, I need to look for this location. Since there is no specific longitude and latitude, I'm going to look for Rio de Janeiro with searching it easily. And then when I zoom into the map, I can see that, yeah, of course it is in Brazil. And then Rio de Janeiro, okay, it is already chosen. Usually the HOMER just finds the location in the middle of the city maybe, but this is the address and this is the latitude and longitude of the location. So I'm going to also add a name for this simulation, exercise 8, and there's no description, discount rate, inflation rate, we just keep them as default, annual capacity shortage, we just keep it as 0%, and project lifetime of 25 years as default. It's good enough. And the question says that daily irradiance at worst months of the year in Rio de Janeiro is 4 kilowatt hours per square meter per day. I don't want to implement and enter exactly this number. We're going to choose what happens exactly with the NASA data. So I'm going to just go inside the resources and then click on solar GHI, global horizontal irradiance, and then since I have chosen already my location, so I only need to click on download from internet, and this is the global horizontal irradiance profile through the whole year, which is average over 22 years between 1983 and 2005. So the question says the worst months of the year has 4 kilowatt hours per square meter per day, but here we can see that 3.66, 3.65 and 3.66. So the minimum number here in worst months of the year, which is May, June and July, since they are in the southern hemisphere, it is 3.65 kilowatt hours per square meter per day. It's close enough to what we have in the exercise, but let's continue with this number, with this new number. So then I need to add a load for my project. You can also see the suggestions here from the software. The software suggests to add a renewable energy source, okay, but which is with the green sign, it means that it is not a must. We can add or we can go with conventional energy sources, but we need to at least enter or add a power source. This is with sign with the red sign, so it means that it's a must, and also there has to be a load for this simulation to work. So I'm going to enter a load. So I'm going to go to the load tab and then click on electric load number 1. I'm going to choose July as for the peak month of the year, because Rio de Janeiro is in southern hemisphere. And then I'm going to click on a blank profile, which is completely free for us, so we can add our load on whatever we want. These peak months, it doesn't work right now, since we are going to enter some load for the whole year, so it doesn't change it through the whole year, summer and winter time, but it was more correct to choose July. Okay, so this is the load profile, which is completely empty now. I'm going to click on show all months here. I'm going to enter the load which is written in the exercise into these hours of the day, and then copy it for all months and all weekends. These 2 check marks must be checked already, which says that if I enter one number here, it will be copied to all the cells to the right, and then also it will be copied to the weekends. So only in this case that we have a uniform load through the whole year, we need to mark these 2 check marks. First of all, one ventilator of 60 watt operating from 9:30 a.m. until 11 p.m. Okay, so here there is no 9:30. I cannot enter 9:30, so I'm going to choose just, for example, 10 a.m. So starting from 10 a.m. I have to add 60 watt. So since here we can see that the unit is in kilowatt, so I need to enter it as kilowatt, so it is 0.06, and that is 60 watt. Okay, so from 9 or 10 a.m. until 11 p.m. So I'm going to copy this number and then add it to 11 o'clock, then add it to 12 o'clock, 13, 2 p.m., then 3 p.m., then 4 p.m., and I will continue until I reach until 11 p.m. Okay, so now all the load values between 10 a.m. and 11 p.m. are equal to 60 watts. So if I click on OK, so this will be our load so far for a day in the whole year. Okay, so but I still need to edit the load. The second types of load is 5 lights of 60 watt, each operating from 7 p.m. until 11 p.m. So 5 lights of 60 watt means 300 watts, 0.3 kilowatt, and then from 7 p.m. to 11 p.m. Okay, so I'm going to add from 7 p.m. here. These cells from 19 to 23 must be added with 0.3. Okay, so it is 0.360 or 360 watt, and then I'm going to copy this to all the hours until 11 o'clock in the evening. Okay, one notebook computer of 30 watt operating from 6 p.m. until 9 p.m. So from 6 p.m. 18 o'clock until 9, these 4 cells we need to add another 30 watt. So 30 watt means 0.03. So that means that I need to change this, add this cell with 0.03. So it means that it is 0.09. Okay, from 6 until 9, so I need to also add 0.03 here. So it means that 390 watt here, and this is the final cell, 390 watt. Afterwards, The final load is one TV set of 100 watt operating from 8 p.m. until 10:30 p.m. So again, I don't have 10:30. I can enter it until 11 o'clock again. So 100 watts, so it needs 0.1 should be added to from 8 p.m. to the rest. So it is 0.490, then exactly 0.490, and then this one is 0.460, and the last one also 460 watt. Everything is also automatically copied to all the cells to the right and weakened, so I'm going to click OK. So this is how our load profile looks like for now, and this is the yearly profile. As we already know, until 9 o'clock or 10 o'clock nothing happens, it's completely zero. Then we have a slightly load around 60 watt, which is only for the ventilator, and then afterwards we have our peak here. You can also see here that the average of these amounts are 2.86 kilowatt hours per day. I also need to add this average in the baseline to the scaled value here, 2.86. If I don't do this, I don't get any results, since HOMER considers this a scale value for an amount of load. But okay, I'm going to put it to equal to baseline, so nothing is changing. There's no efficiency for the load, nothing else. So let's go to see the plots, for example. Here these are the monthly scaled monthly averages. We don't care about that. Profile here, exactly. So you can see that all the profiles in all months are exactly the same, but this is what our load profile looks. This D map is exactly the same as this one. Histogram is also like this, and then we go to the next part. So now we need to add our battery system. It says that calculate the battery size. So I'm going to choose the battery. In the components, I can click on storage button here, and then I will choose to keep this generic 1 kilowatt hours lead acid battery as what it is right now. I can also choose lithium ion or other types of storage system, but let's go with this one. I'm going to add storage. So the battery size, the battery system voltage should be 24 volts. So it means here it is 12 volts already. So I need to add a string of 2 batteries. So it means that 24 volts. And battery cycle efficiency is 8 or 80%. I can find the round trip efficiency of the battery here is 80%. It's not possible to edit this number, but it is exactly by luck what we want. But you can choose other types of batteries, and then they also have different efficiency, but this one is good enough for us. Then let's go to efficiency of charge controller, and inverter efficiency is also given in the question, but I also need to edit these numbers in the parts, in the coming parts. Everything with the battery looks good enough for now. So let's add a PV system, our previous modules here. I'm going to exactly again keep generic flat plate photovoltaic modules. So I'm going to click on add PV. I can see that the rating factor is by default 80%. Yeah, lifetime is 25 years. That is correct. Yeah, I need to enter the efficiency of the PV panel at 10%. So I'm going to click on advanced here. And then let's go to the temperature tab. And then I need to check this consider temperature effects check mark. And here efficiency of standard test conditions is by default on 13%, so I'm going to change it to 10% depending on what the question says. And in the question there's nothing about temperature coefficients or temperature effects on power, so I'm going to change it to 0 just to correspond our simulation to the exercise. And about the charge controller, there is this efficiency of 95%, but we don't have charge controller in the components of HOMER Pro. We have a controller which is something else, and we have a converter. Usually the charge controllers can be considered with the battery systems, but also in HOMER there is not this possibility to add this charge controller inside the storage system. But there are many devices, there are various MPPT controllers or MPPT trackers available now in the market that they have the MPPT function and also the charge controller function. So I'm going to consider this amount of efficiency in the maximum power point tracker. So here it says explicitly model maximum power point tracker. I'm going to tick this check mark, and then the efficiency is 95% by default, so it's what we need. And yeah, nothing else. About the orientation, I just keep what the program suggests afterwards, and then I'm going to click on OK. Efficiency of the PV is also added. Next part is the efficiency of inverter. So as you can see, there is also 2 errors here. I need to add a converter or inverter since my load here is AC on AC side, of course, and PV and battery both are on DC side, and I need to connect these 2 bus bars with a converter. Okay, so I'm going to click on the converter here. Yeah, there's system converter is already chosen already, so I'm just keeping it like that. And the inverter efficiency must be 90%. So I say inverter input efficiency here is 90%. And about the rectifier, I also put it 90%, but we don't use that much. And I guess that was it. You can also take a look at the question here. Okay, so yeah, that's it. Let's now continue. Okay, I need to also add the costs of the components to the system, so I'm going to click on PV panel for now. Let's change the unit to euros instead of dollars. So let's go to here in the project, and in economics you can choose euros. Okay, so let's go back to PV. Now all the units are in euros. PV panel including duties and taxes must be 1 euros per watt peak with lifetime of 25 years, which 25 years is already added here, and 1000 per kilowatt. Okay, here 1 kilowatt is 2500 is already added by default, which is too much for us. But I will also add the mounting and support structure cost, which is 50 cents per watt peak. I'm going to add 1500 euros for each kilowatt, and then for the replacement also the same price. Operation and maintenance, I'm just keeping it as what it is now. Okay, the final part is to add the price for the battery systems and its lifetime. So I'm going back to our battery system, which is here, 1 kilowatt hours lithium acid battery. Lifetime here, it is 10 years by default, but I'm going to change it to 4 years as what the question says. And the capital price for 1 kilowatt hours, which our capacity, nominal capacity, is also 1 kilowatt hours, so it's 300 euros, which is the correct number. So I'm going to keep it and not changing anything else. Okay, so now we can maybe run the simulation. One more thing is the error here, define temperature for PV. Since we have chosen to consider temperature effects for the PV as well, program also gives us this error and we need to download the temperature data. But actually I have chosen temperature effects on power as 0%, so in the end there's no effect from the temperature, but let's download the data so it will be, so that the error will be gone. So let's go to the resources and temperature, or let's click on the error itself, so it just guides us directly to this page. I'm going to click on download from internet, that's it. And you can see that in Rio de Janeiro, the average temperature in January is 25, and then in our summertime or in their winter time it will be around 19. So yeah, that's it. So let's restart the simulation. So if I click on this calculate button here, the simulation will be happening. Now you can see these different cases, and then okay, so it automatically goes to this page. There is a summary page and table and graphs. I'm more comfortable with this view of the results. So it means that this line is one scenario, okay, and it is categorized, and this check mark for categorized is checked here. So if I click on overall, I can see many different scenarios, but all of them include PV, battery system, and an inverter. Okay, so I'm going back to categorize, because the categorize will choose the best one and then the cheapest one with all the scenarios with same components. So this one is the cheapest one with consisting PV panels, storage system, and the inverter. But for example, if I had a grid also connected to the system, these options will be more, since the grid and the battery and the inverter can also be another option. The grid, PV, and battery could be also another option, and there are multiple options as well. So, but for now, we can see that there's only one option, and this is the cheapest one with these components. So, okay, the simulation tells us that we need 1.8 kilowatt of PV panels. It is 1800 watt peak. Then this is the column for our battery. We need 14 batteries, each with nominal capacity of 1 kilowatt hours. Okay, this column of PV MPPT shows the results for the system with the maximum power point tracker. Of course, it helps us a lot. It means that instead of 1800 watt, we need only 1000 watt of PV modules, and it's a really good saving. And as I said, yeah, 14 batteries of 1 kilowatt hours is needed. The converter of 813 watt is needed. This NPC is a net present cost, and it is equal to the costs of the whole system for the whole period of its lifetime, if we want to pay all the costs in the beginning of the installation. Okay, so, and this all the scenarios are sorted according to net present cost. So if I click on overall here once again, I can see that, yeah, this NPC is going higher and higher for other cases, but of course with categorized view it shows the best one and cheapest one. COE is cost of energy. It is a cost of unit of energy. For example, in this case, for every kilowatt hours we need to pay 1.54 cents, 1 euros and 54 cents, which is really expensive considering that we can buy the electricity from our grid with numbers around 25, 28 cents. Okay, but now if we want to limit ourselves only to PV energy and the battery systems, the system costs 1.54 cents for every kilowatt hours. There are other columns as well and other informations, of course, like operating costs with unit of euros per year. Renewable fraction, of course, it is 100% since we don't have any conventional energy sources. Then we have the capital cost, production, kilowatt hours per year, autonomy of the battery systems, which is 70 hours. It's around 3 days. This is days of autonomy. And the thing is that in HOMER we cannot enter these days of autonomy on our own wheel, but the program suggests it on its own after running the simulation. And yeah, that's it. But if we double click on this case, so it will go to another window and shows us more information. So the first one is about the financial aspects of our project. This is net present cost. The most cost of the system is going to be dedicated to the battery systems. Here, generic 1 kilowatt hours lead acid battery is has the highest price through our whole system, and then the PV modules, and then finally the system converter. There are other financial and economical tabs here. I'm going to click on this electrical one more time and then see that the production of flat plate PV is 2,200 kilowatt hours per year, and it was 100% of the whole production in this system. There is no other energy resources. Exactly, renewable fraction is also 100%, and then this is the share of PV production through the whole year. In August was this much, in March was this much, and for example in January was also around 0.17 megawatt hours. If there was other energy sources, so here this table, this diagram was also divided into different energy sources as well. I'm going to try it soon one more time. Renewable penetration is another part, so you can see that in these diagram you can see the penetration of renewable energy through the whole year by various parameters. And then if I go to the generic 1 kilowatt hours lead acid tab, it shows me different information about our battery system. So as we said, 14 batteries, we need 2 batteries in each string to have the 24 volts. Then 7 strings in parallel we need. Days of autonomy is around 3 days or 70 hours. Nominal capacity, these are the stuff that we don't care about that much right now. The frequency of the state of charge of the battery is also like this. So it says that most of the time the battery is charged until it has the capacity of 76%, and as we wanted, it doesn't go less than an amount of 54%. I guess in the simulation was 40% as minimum state of charge, but we can see that in real simulation it didn't even go less than 58 or something %. And then you can also see the state of charge of the battery through the whole year and through the hours of each day. You can see that in the hours in the evening the battery is almost full all the time, and then in the mornings the battery is half empty or is 77%, for example, in this case. It means that during the day, which the irradiance was good enough, the battery was getting charged, and then in the evening, starting from 12 o'clock or until 18 o'clock, the battery is almost fully charged. Okay, the next step is about our PV modules. You can see that the PV power output is also illustrated in this diagram for all days of the year and then all hours of each day. And you can see that exactly based on the input data for Rio de Janeiro as the input irradiance data. So you can see that only between these 2 hours we have irradiance, and these are the times that our PV modules had some outputs. Next step is about our inverter. So you can see that this inverter output, and this is the rectifier output, since we are always working with the conversion of DC electricity to AC, so we can only see this diagram for inverter. For rectifier there's nothing. And final one, if we go to the emissions, since we had only renewable energy sources, we don't have also any emissions. So carbon dioxide, carbon monoxide, sulfur dioxide, and all the harmful emissions are set to 0. Okay, so now for the second part of the exercise, I'm going to change our numbers for the load only for those lights of 300 watts from 7 p.m. until 11 p.m. and I will substitute them with 40 watts since we have 5 LED lights of each 8 watt. So I need to go to the load part again here, and then I will open the show all months here, and by changing our conventional lights with LED lamps, I need to reduce our load from 7 p.m. until 11 p.m. with the amount of 260 watt. Okay, so I'm going to find 7 p.m. until 11 p.m. which is from this cell and the final cell, and then reduce these for 260 watts. So this one will be 130 watt, this will be 230, then again 230, then this one will be 200 watt, and this one also needs to be reduced by 260 watts, so it is again 200 watts. Okay, and so all the new values are updated through the whole year. So I'm going to click on OK. I can see that the load profile has also changed, and I can see a sign here which model does not match results, and I need to recalculate my simulation. So I'm going to rerun the calculations. Okay, we can see that there is a new case here. The numbers are changed, so we're going to briefly just compare them. So first of all, in the older case with the normal lamps or conventional lamps, the PV modules were about 1.8 kilowatt, and now they are at 1.91 kilowatt. Okay, this is strange because we have reduced our load, but the PV is simulated as a higher number. And for PV with MPPT, it's again still on 1000 watt. Before was also like this, but the battery in the older system was 14 battery systems, and now it is 12 kilowatt hours. So 2 of the batteries are gone, and batteries are really costly, so it means that our system should be a bit cheaper. Okay, then let's go to the NPC, net present cost, and our older number was, I have written it here, 21,000 almost to 20,700 euros, and now it is 18,400. So it means that around 2,000 euros or around 3,000 euros is less now. And then cost of energy for every kilowatt is reduced from 1.54 euros to 1.37 euros. Okay, so this is the amount of saving that we saw through HOMER about the costs. Amount of loads, as in the exercise also says, the amount of load is 86% less than before, but the amount in the cost of the system after the simulation in HOMER, it is much less than this amount. Just to show you another small example, I'm going to add, for example, a grid to the system, so the system is not off grid anymore, it is also connected to the grid. And then grid power price is 10% here, so I'm going to change it to 20, for example, which is more realistic. And then if I can sell back our extra electricity to the grid of around, for example, 10 cents. So this is a normal grid. I need to calculate the system once more. This time I expect to have 2 rows of results. Yeah, we need to wait a bit. Okay, I have even 4. So let's see. As I said, the view is categorized here, so each line has a system with different unique components. Okay, not any of these 2 lines have exactly the same components, but if I click on overall, this will change and all the cases with different components will be shown. So I'm going to choose categorize once more to see the cheapest scenarios. The cheapest scenario is the first line right now with a PV module and connected to the grid with no battery system and also an inverter that we need. So the PV panel in this example will be 290 watt, which of course is maybe 1 or 2 modules, so it's not much, but it's just to have some renewable energy in the system. And you can see that there's no battery, 0. Let's go to the net present cost, and the costs are 2,500 euros. In our previous examples it was around 18,000 or 20,000. Okay, so and also you can say that the cost of energy is around 16.7 euros, sorry, 16.7 cents per kilowatt hours. And if I open on this scenario, I can see that, for example, in this case, electrical, I can see the share for the production of each of our sources for each month. Of course, the grid was had the main share of the production, and PV had the smaller one. And then renewable penetration, you can see that, okay, what happened and at what times of the year we had some production from our PV panel. And then you can see also in this diagram, of course, the PV panels had a low amount of production since there was only 290 watts, and that's it. So the second option is the option only with just the grid, nothing else, no renewable, no other stuff. So you can see that, yeah, as we entered 20% for each kilowatt hours, that cost stays the same. But through the 25 years we need to pay this amount of net present cost for the whole system, for the feeding of the whole system and our loads. Another case is with all components, as we talked before. Yeah, but this time the PV is also a low number, and the price of COE, the cost of energy, is 33 cents, and it's still too high. And the final option is with the grid and storage system and no PV. And this means that this is also the worst case, or the highest, has the highest price in these examples. You can see that the cost of energy is 38.5 cents per kilowatt hours, which is too much. Yeah, as I said, you can play with all the components. You can add wind turbines as well. You can do whatever you want, generators. you can continue playing with the software and get interesting results. But the target of this tutorial was to get you familiar with this software. There are various softwares that are doing almost the same things as HOMER does, but HOMER is a really good and professional software for this matter, and I hope you have learned something for it. Thank you for your attention, and I wish you good luck.